Hi, hello, namaste. In the last video, we derived Ehrenfest theorem and we saw that the time evolution of expectation values in quantum mechanics looks similar to Newton's laws. And we got something which looks like this after the derivation. The conclusion looked like this, where the left part the left part indicates the time derivation of expectation value of an operator, right? And on the right side we have 1 upon IH cut and the operator which is in commutation with the Hamiltonian. So operator commutating with Hamiltonian on the right side. Now a question that of course arises is that does this mean that quantum mechanics gives classical motion? Because this whatever we got in the Ehrenfest theorem, it looks very similar to some sort of a classically related equation. So the question of course is very natural to occur. So how do we tackle it? So of course again I'll write the question that we are going to lead in this video is that does this means that QMech or quantum mechanics gives classical motion So this is how, and how we are going to answer this. We are going to answer this using the Ehrenfest theorem. We are going to use Ehrenfest theorem with what? We need a system to use Ehrenfest theorem. What is the best system that can happen with it? So the system which we are going to use is very common, and it appears almost in every physics problem you come across. So it is basically called the harmonic oscillator. So we are going to work with harmonic oscillator as a system using Ehrenfest theorem. We are going to use this equation to prove it, and from this we are going to get two equations. So we are going to first go through this part and then we are going to get to the conclusion of the harmonic oscillator part. So first we need to construct two equations. What we do is, let us take this operator A, let us choose or give some value to this operator A. So we choose that my A should be equal to X. A should be equal to X. If my A is equal to X, that means we are just going to solve this part first. So I'm going to solve this part, which is X and the Hamiltonian. Okay, we know that since we gave A as equal to X, we also need to know that what exactly is H. H is the Hamiltonian, which is given by p square upon 2m plus v of x. Okay, now we try to construct this in this particular commutator. So my x, right, which we chose, and p square upon 2m plus v of x, and then we are going to commutate with each other. So x comma p square upon 2m plus x comma v of x. Well, this becomes 0 immediately because this one actually both of this depends on x. Both depends on x. So it immediately becomes 0. Now, what about the other one? So the other equation was x comma p square upon 2m. So we can take 2m outside, and this is x comma p square, where x comma p square actually is a value which is given by 2I h cut p, and it is also same for y comma p square, and it is also similar for z comma p square. So what we do is we cancel 2 from both sides. I mean, not both sides, but as since they are in upon. So what we are left with is I h cut p upon m, right? Now, of course, we get back to the original equation that my d by dt of this x operator, expectation value operator, is equals to I upon h cut. I'm sorry, it's not I upon h cut, 1 upon I h cut into, we got this value, right? So we are going to multiply it here, which is I h cut, and we take p in the expectation bracket, and so what we do is we cancel it again, and we get p upon m. This is first part of what we got in the form of equation. Now we take the other part. Now we will take the other part where I will tell myself that let me choose my a to be equals to p. Okay, so if my a is equals to p, then how does this equation becomes? So d by dt expectation p is equals to 1 upon I h cut, and the commutator is p comma h. Where I'll just solve for this part first. So p comma h. So of course, again, p comma p square upon 2m plus p v of x, where we will get this part as 0 because these two are p in the same commutator. So what does this gives us? This gives us a very nice value, which is minus I h cut dv by dx, and we know that I can write my dv by dx in the form, I can write this as basically v dash x. So I'm going to write it as minus 1 upon h cut v dash x. So my basically p comma h, or p commutating h, becomes minus I h cut v dash x. I'll put it in the main formula again, which is d by dt, where we took my a as p now. So 1 upon I h cut minus I h cut and v dash x, which is going to be equal to, as this both gets cancelled, so this is minus v dash, which is in expectation bracket, of x, which is my d by dt p. Now since we got both the values, we are going to write it together and we will solve further. Now if we recall my first value, which was when we took a as x, it was this, and my second value where we took a as p was this. Right? Now with this two very important and helpful formulas, we are going to construct our further and final form of equation. So what we do is we are going to differentiate this equation. We are going to differentiate this equation with respect to x. So differentiating, I'll call it, let's say, equation 1, and this is equation 2. Now differentiating equation 1 with respect to x. So of course you know what it is going to be. So d square upon dt square, the expectation value is equals to 1 upon m d by dt and p. Now if you recall, this we got as v dash x in negative, right? If you look closely, this is what we got. So we are going to just put it inside, I mean this value in this part of the equation. So it becomes d square upon dt square x is equals to 1 upon m, but it is minus now v dash x. Now if you recall something which is very, very major and important, you might have heard about it in your lower standards, that the value of harmonic oscillator is basically given by v of x is equals to 1 upon 2 m omega square x square. Now since we have v dash, right, we are going to differentiate it with respect to x. So v dash of x is going to be m omega square x. Now since we got the value of v dash, we can put it in this equation, right, and we will get something really nice. So we are going to substitute it. I'll say that we are going to substitute it, and it will be d square by dt square is equals to minus 1 upon m omega square x. And since only x is going to stay in this expectation value bracket, so minus 1 upon m omega square x, this to this gets cancelled. This is going to be minus m omega square, this is going to be minus omega square expectation x. So the final form of equation looks like this. So d square upon dt square expectation x plus omega square expectation x is equals to 0, and we are just going to bracket this up. What does this tells us? Okay, so this shows that for an harmonic oscillator, the average position of a quantum particle, it follows the same equation of motion as of classical. It's very interesting because you have seen this equation in classical mechanics. Now you are also observing this equation in quantum mechanics. So does this mean that they are both acting similarly? They are both acting similar. That means whatever we observe in classical world is what we get to see here in quantum world. The question arises, and if it is true, right? So obviously this result actually comes directly from quantum mechanics without any the approximation which we always take, some approximation or some average value, but this comes directly. Okay, so the question arises, are they going to act similar to each other? What we observe in classical is what we are going to observe in quantum mechanics? No, definitely not. Because the system itself is still in quantum, right? This system is still in quantum. We are not going to observe things similar to what we observe in classical mechanics, which has properties, right? If I can write some properties down there. So we know that even if it has similar equation, it still has something like discrete energy levels. But the average motion behaves classical, right? It means that the average motion behaves classical. The average motion behaves classical. Why, if you may ask? Because the force is actually the force is directly proportional to its position in harmonic oscillator, right? Therefore, the harmonic oscillator, it clearly shows that how this classical, the classical motions, it emerges. It of course emerges from quantum mechanics at the level of expectation value. At the level of expectation value. And with this, thank you so much for watching.